Hi, I'm Christian. I'm a data all-round nerd. Used to be a physicist, but do consider myself like a long-time Unix nerd, and nowadays I'm building a Kubernetes-based MLOps platform. On the right here, you see my co-author and colleague Henrik, who unfortunately couldn't make it here today, but whom I created this presentation with together. This whole thing, though, is based on a more or less scientific paper which was published in a scientific journal. Here you see some more of the author, or all of the authors of that paper, but I want to stress that there are quite a lot bigger team, or it's a bigger team involved in the whole work we are presenting here today. And obviously all of this wouldn't have been possible without them. Before we come to, so to say, the meat of this talk, I want to quickly give you an overview of where all of this is coming from and why we have the ISS in the title of this talk. So I guess most people here have heard of the ISS, the International Space Station. You see it here on the left part. And one part of that, unfortunately, I can't really tell you which one, is a European module called Columbus. Some space nerds perhaps can point that out later on. And as you can hear from that, I'm not really a big space nerd, though. But what's special about a space station? Well, space is a very hostile environment, and so you want to make sure that it really always works as intended, because otherwise people might die. And like the central part of that is the life support system. And what we developed in this KISS project is a system to do anomaly detection, diagnosis, and reconfiguration for this European part of the International Space Station, especially the life support system. The project is funded by DTEC BW, the European Union, and project partners you see down here, 2 universities, Airbus, Just at AI, and ProCube. And before we get into that, perhaps what are we going to talk about today here? So first, I'm going to give you a high-level overview of our use case so that you just understand where we are coming from, what kind of challenges we had. Then you're going to learn which part of Kubeflow itself and also the wider ecosystem we used to implement this use case, how all of that fits together, and then some challenges, solutions, tips, and tricks. Unfortunately, there are also some things I'm not going to talk about, and if you're only here of the ISS, I'm somewhat sorry that I baited you, and now's your time to leave, because we're not really going to talk about any parts of that. We're also not going to talk about any of the scientific methods, how the anomaly detection works, the reconfiguration, and so on. Also, nothing about large language models in here, no model context protocols, and also no agents. If you came for any of that, also still your chance to leave. I won't judge you. Good news, though, on the scientific methods and results. In the end, I'm going to present some QR codes, and if you're really interested in that, there's some papers linked and so on, and so you can really nerd out as much as you want on that front afterwards. So let's come back to our use case. So we have one use case that's made up out of several steps. So we have time series data coming in on the left here, like there. Then we do an anomaly detection. If that found any anomaly, we're going to do a root cause analysis. Then reconfiguration, so how should we reconfigure that? An example I give, which is really the only one I've heard about, is like if, for example, one of the fans doesn't spin fast enough anymore, like an easy solution would be spin another fan faster to make sure that air is flowing like in the right amount. Obviously, that's a very, very simple thing, and there are much harder and more complicated things that you can reconfigure to get back into a safe and good configuration. And then finally, there's the supervision part, which makes sure that something that the system suggests is also really safe and the way to go there. We use Kafka to tie all of that together, but to be honest, that's also just like an implementation detail. We use KServe for all of those 4 different components. and then Postgres and timescale databases to store all of that, but that's also not what this talk is going to be about. There's a nice little dashboard which shows the operators, what these algorithms found. So also, at least for the moment, none of that is like completely automated, not only because this chain of Python codes found something, the ISS won't be reconfigured, but some people actually need to press a button still, which is probably a good thing. You also see one thing here. It says placeholder here, and unfortunately, I can't show you any of the real data, also not of the real dashboards and so on. But at least for the purpose of this talk, this doesn't really matter at all, because we provide basically an analog to the real code, which we also have up on GitHub, and it's also linked at the end, which works more or less exactly like the real thing, and you can use that to start your own use cases from. And it's basically a bit cleaned up even version with some of the scientific parts removed that some people felt uncomfortable to let into the open public. The part that we're going to mostly talk about today is the anomaly detection, and mostly because that's a classic, so to speak, or what we nowadays perhaps call classic machine learning, so neural network, and all the other parts are like old school AI, so symbolic AI, and we don't really need like any pipelines for data preparation and so on for that. So today, this is the focus. And with that, we do face quite some typical ML challenges like distributed preprocessing, hyperparameter search, multi-GPU modeling, model deployment, and finally, we want to tie all of those things together in one like complete workflow. We use Kubeflow, which lives on top of Kubernetes as like the main center and also of tying all of that together. But Kubeflow alone wasn't really enough for this use case, so we also use MLFlow for registering and tracking our models and experiments, and also Dask for like really big preprocessing tasks. And I guess you guessed it already on the slide before, for all of those challenges, we are now going to talk about how we solved that and also which tool we used for that. So from like the left to the right, that's Dask for multi-node preprocessing, that's Katib for hyperparameter tuning, the training operator for multi-GPU model training, because like everybody, I guess nowadays, can use a GPU. It's PyTorch or something like that makes it really, really easy. Even using multi-GPUs is pretty simple, but it gets a bit more complicated if you want to use multi-GPU on multiple hardware machines, and that's where that part comes in. Then we want to deploy that model, and finally, as mentioned before, we want to tie all of that together. So let's start with Dask and the distributed preprocessing. Are there any Dask users in the room? Very few. So Dask is like a, I'd like to call it like a Pythonic replacement for something like Spark, which at least makes me and also most of my colleagues a lot happier than using Spark. And so why did we need to use this? We had like massive amounts of data which wouldn't even fit in memories of really, really beefy machines. And while it's not really part of the Kubeflow ecosystem, it can be run on Kubernetes pretty easily. And it's very easy to set up, or at least it's very easy to use once it's set up on Kubernetes. And I'm going to show you the second part, so how to use it once it's set up. So we now also in the future going to see a bit of Python code. All of that available on GitHub in the end, so while you can obviously take pictures if you want, you can also just download it on the end on your computer and have a look at that in more detail. So we see here at the top, we do basically two small imports from Dask and Dask Kubernetes. And then, so all of this is wrapped in a class, but it's not really that important here. We create a new kube cluster. We can scale it to a number of workers, so that really depends on how big our cluster is or how much compute power our cluster admin allows us to use. And then we can connect the client, and if you know Dask, that's basically already it, and then you can like Dask as much as you want. So yeah, so if you then call Dask operations, they will just be executed on the cluster and also be map reduced or whatever you use on there without you needing to know any of the details, which our users think is very, very nice. And so like one small diagram here. So we have this Dask operator there, which then creates a scheduler pod, and that creates a Dask worker group, and that creates like lots of workers. And it also has a nice UI, which you can open, which looks like this. And so we see here, this is basically like textbook map reduce. Each of those colorful dots is one processing step. It goes from the left to the right again. And the different colors here show you what's currently happening here, so from queued to already released. And all of that, as I said, works on Kubernetes. Next part, hyperparameter search. So here we're going to use hyperparameter search pretty much in the beginning of our workflow, basically to find good starting parameters for then the proper training of the model. And for that, we need like three things: a training script, an image or Docker file, and then an experiment YAML. And from now on, we are also going to see quite a bit of YAML, but that's just the way, unfortunately, that Kubernetes works. And while it's a bit ugly, at least in my opinion, you get used to it. So let's start with the training script. Here we have some small parts of Python code. You see it's like up here uses, so there's a function called run training, which is like some click decorators applied to it, which tells it some things. So for example, how many GPU nodes to use to run PyTorch job or not. Here the mostly interesting thing is this parameter LR, which is what we want to optimize, which is the learning rate. And then also again here, the most important thing is this trainer thing, which we initialize. And then you can see here we can use MLFlow autologging, so that we have a nice web interface afterwards. And afterwards we could basically use whatever we want to run our model. Second part, I said, we need, well, in the end we don't need a Docker file, but we need a Docker image, but you can generate that from the Docker file. So here we use like Python 3.11 as a builder. We install everything in there in this builder image. We create a final image from that, where we then, after we've installed quite some things, copy our code, which I've shown before, into this image, install everything, build it, push it. I haven't shown that here, but then can use that later. Third thing I mentioned was this experiment YAML. And so here we see for the first time now, I believe, a YAML file and a Kubernetes manifest to be specific. And what you see here at the top, if you've never seen that, it shows us which API we use. So this is a Kubeflow experiment. That is what it says in the line below. And then the more interesting stuff comes afterwards, the specification. And here we say we want to run a maximum of 10 trials, 3 of them at maximum in parallel, maximum 3 failed ones, then we want to abort because then probably something went wrong. And obviously this is only an example, and if you need to run 10,000 experiments, that's also fine. You can just put 10,000 in there and it just works. Sorry, lost my train of thought there. So you don't need to really do all of that in that YAML. If you really dislike YAMLs, there's also a nice web interface built into Kubeflow, which you can use. But it basically does exactly what we just saw. And while it's perhaps nicer to try some things, at least if you want to put it into version control afterwards, we really recommend using the YAMLs, even though it's ugly. So then we need to tell Katib what it should actually do. And here we say we want to minimize this validation loss, and we want to use this random algorithm, which obviously is, or perhaps not obviously, but might be a very bad choice, might also be the right choice. In this case, it's just there as an example. So Katib supports lots of different things there, and you can do something more involved there as well. And then here at the bottom, we say, so which parameter do we really want to optimize the learning rate? It's discrete. Here there's a list of possible values down here. So you could just supply all of them by hand. You can also, there are also some ways to say like, it's going to be between 1 and 2 or something like that. And then it will automate that. And while it's very simple to do that for one single parameter, as in this example here, you can also optimize lots of different parameters at the same time, which is probably what's a lot harder, at least for the code to do. Then here at the bottom, we tell it what should it actually run. This is also where now our image comes in a second. First, you see here at the top, this is basically one manifest put into another. So this here is this job file. This is the image that we're going to use, and we want one GPU. And then this is the Python command it should run. And down here at the bottom is our learning parameter, and Katib extracts that automatically from the output of our Python script that we run. We have an experiment controller which creates a trial controller. There are lots of workers. Again, we can do as much as our hardware or the administration people allow us. And then finally, there's also a very nice GUI which allows us to see in the end which set of parameters was the right or the best one, and we can see here this more real-life example has several parameters it tries to optimize at the same time. This brings us to multi-GPU model training, and we also need 3 things. As before, a training script, an image, and a PyTorch job YAML, but the good news is the first 2 we already have, and we don't need to look at again, because we can use exactly the same as before. And so how does a PyTorch job YAML look? You're probably now already a bit used to how these manifests look. So API version is Kubeflow again. This now is a PyTorch job. And at the bottom here we can say how many replicas to run at the same time. We tell it which container to run and also which command to call. We can say like 2 replicas at the same time also. Also some more details here we can set. So in this here, we track it in MLFlow even. We call it Eclipse variational autoencoder training, and then track the whole thing in MLFlow. We're going to see in a second how that could look. And the nice thing is, without doing anything else, PyTorch job and Kubeflow trainer use this distributed data parallel algorithm here, which you might have heard of, which is used to do this train models on multiple nodes at the same time. And then we could hopefully observe something like this, where our validation loss like more or less continuously goes down during training. Which brings us to the next one, model deployment. And here we also need like 2 things now, a trained model, which the step we before had created, and a KServe YAML. The KServe YAML is a YAML again. We've seen some of that. So this time it's an inference service. We tell it, or give it a name, which also should be familiar to you now. We tell it where to load the model from, which we can get from the MLFlow UI, which you can see here. And then we tell it, well, you should try to get 1 GPU. And that's basically already it. If we apply this manifest, again in the Kubeflow user interface, we can see all of those things we just put in, and we also get some monitoring basically for free if our administrators set up all of that correctly. Which brings us to the last part, workflow orchestration. And as said before, those Kubeflow pipelines can be used to get all of that together in one workflow. In the user interface, it might look like this. This is the upper part of our workflow here. This is the lower part, and you probably can't see anything, at least from the back, so I zoomed in a bit. So you see here these things which have a blue bubble on the left are tasks or components, and the yellow ones are artifacts which were generated by those. And we can create those components or tasks in several different ways, and we're just quickly going to talk about the simplest way, the so-called lightweight components, also because this is a Python conference, and this makes it very easy to create one of those components in Python. So as before, we have a function here. In this case, it's called evaluate model, so it's just one example, and you can basically do whatever you want in there. And we tell it which base image to use, which here so we use a Python image, and it has some things installed in it which we like, but for basic images, you can also just use Python in whatever version you want. And then we tell it here you want as an input the output of a previous task and an input data set. And at the bottom here, we can see then we can basically do whatever we want in here. So in here, there's this model evaluator, which is part of the base image we use, but you can just write whatever Python code you want in there as long as it's in one function, which obviously is quite a big limitation, but for small things, these lightweight components still work very well. And otherwise, you can do what we did here. You build one big image which contains all of your Python code you want anyway, and then call those functions just in another function. And all of that then is supported also by the user interface. So for example, here we see this output of the previous model we got. We see this output artifact, which helpfully here it renders our Parquet file like as binary, which, well, isn't too helpful to be honest, but at least we see it's a Parquet file, which is good, I guess. This brings us already more or less to the end. So what we've shown here today is how we tied all of those things together to face some practical challenges we had in this project. If you wanted to have some take-home messages, I would suggest take those three. So the open source ecosystem provides solutions for all steps of the ML lifecycle, which is a good news in my opinion, because if you don't want to, you don't need to use tools developed by, I don't know, Google, Amazon, or whomever, but you can use all of those things in free and open source. Kubeflow makes a lot of those things really easy and some things possible. But it does mean you need to use Kubernetes, which might be worth it or might not be worth it for you. That's probably something you only can judge. And then if somebody has set that up for you, data scientists can really scale machine learning workloads to massive scales without knowing a lot of Kubernetes, but only those small YAML things, and that's all in the documentation I've shown you before. I saw some of you people already getting out their phones to scan those QR codes here. As mentioned before, this is like the proper code which really runs, which I've shown some extracts from before. There's a paper explaining the scientific parts more in detail, and if you're more interested in how all of this works on the Kubernetes side of things, we also gave a talk about this last year on the Kubeflow Summit, how we made all of that possible. And with that, I'm at the end of my talk. I think I used really up all the time.
We do have 5 minutes for questions.
Perfect.
We can answer 2 questions. So the first one is how many people are maintaining and giving support to the platform, and how many users?
So users to count as a a bit hard because it's deployed like at several institutions, so at 2 universities who use it also not only nowadays for this project, but also for other projects. At Airbus, we use it for development purposes, but I would say like probably for this project and like very related projects, 20 to 40 people more or less regularly. And maintaining is also not that easy because a lot of people, like also me some time ago, do both things. So they develop and maintain this platform, but they also work on the use cases. But you probably to build something comparably, probably like 2, 3, perhaps even 4 people to keep that running all the time.
All right, so last question. Can you comment on using Kubeflow versus Prefect for large machine learning ops, MLOps projects like the one discussed? And
what
especially
was the second one? Refect?
Prefect is another orchestration tool instead of Kubeflow. And
no, I can't. Sorry, I don't know that.
Are there any other solutions for abstracting orchestration?
Yes, lots of them. So basically, well, I used to say everything with flow in its name. Nowadays, I think all of those ops to agent tools also have flow in their name. But yeah, there are really lots of solutions for that.
Right. So, is there any questions from the audience here? We still have 2 minutes. If not, then another applause. Oh, we do have.
For hyperparameter tuning, do you have any thoughts about Katib versus Optuna versus other tools?
Yes, but like at least Katib versus Optuna isn't really a choice because Katib can also use under the hood Optuna. So a lot of those tools I also talked about before didn't start from scratch, but they looked at what things are already there. And so inside of Katib, you can choose several different optimization frameworks, and Optuna is one of them. And in this special case, Katib is really just doing the Kubernetes part, and it doesn't really do the, so to speak, the hyperparameter part, but it uses other tools for that job.
We got another question. We still have time. How do you do monitoring and observability?
We also use open source stacks for that, so like Grafana, Prometheus, Loki, Jaeger, and all of that stuff.
Great. Thanks a lot. Then we're finally.
Thank you.